Hello everybody and welcome to my presentation about the FDS pressure equation, which is a very important equation in FDS and which particularly poses a major challenge in terms of an efficient parallel execution. So I'm really happy to be part of this great event today, and before I start I would really like to thank the organizers for making it possible for the FEMTC to take place in this perfectly organized way despite the very difficult conditions. So for all of you who don't know me yet, my name is Susanne Kilian, I'm a mathematician and I'm part of hhpberlin, which is one of the biggest fire safety companies in Germany. So there I'm responsible for the use of FDS, and besides I have been working for many years on the parallelization of the FDS pressure equation in a long-term cooperation with the main developers. Now, what's the agenda of my presentation? In the first part, I would like to briefly give you a formal description of the FDS pressure equation. But don't be afraid, apart from a few formal slides that are just necessary to introduce the topic, I promise that I do not want to bother you with too many mathematical formulas, but I would much rather like to give you an intuitive understanding of the very special intrinsic properties of this equation and especially draw your attention to the consequences they have in terms of efficient parallelization. Then in the second part I will present some of the most fundamental design principles that underlie the different pressure solvers, and finally I will present some selected pressure solvers in a very illustrative and intuitive way just to make clear their basic modes of acting. So here it is. This is the special form of the pressure equation as it is used in FDS. So it's not important to understand every single detail here. I only want to make clear for what the different terms stand for. So I will briefly try to give you a picture on the meaning of these terms. The first term on the right-hand side shows how the velocity field, u, is influenced by all the thermodynamic quantities. So actually here the heat release rate comes in. And the divergence of the velocity field, that is this term here, is one of the most important quantities in FDS, and its treatment is enormously complicated and is associated to the energy equation. And the second term here, with this big F, subsumes multiple effects, for example gravity, particle drag. So imagine you have a sprinkler system, then the water droplets drag away some particles and induce a flow. And besides, the entire topic of turbulence modeling is hidden in this term. So the treatment of these two terms is extremely complicated and it fills many pages in the technical reference guide, and I am in the lucky position that I don't have to compute that. They are both provided by the surrounding FDS code, and I simply get the complete right-hand side, which I will abbreviate to R. The only thing which is important for me is this remaining term, which from a mathematical point of view is an elliptic partial differential equation of second order, which is also called Poisson equation. And now I'm interested in this special term, in this del squared h, and I would like to explain it in more detail what this term really means. So this h is defined as the Bernoulli pressure, and based on the low Mach number assumption, which is a very basic design principle of FDS and which assumes a subdivision of the pressure into a background part which only accounts for the stratification in the atmosphere, and a perturbation part which is related to various acting forces, such as, for example, heat or air introduced into the domain. So this h is only related to this perturbation pressure. And this is the part of the pressure which actually drives the flow. And this is the only part which we have to deal with in this equation. And now, if we take a look how this term was generated, then we see that it was created by taking the divergence of the gradient of h. But what does that mean? Here lies the key for a deeper understanding of this term. So imagine you push air into your domain, or that you ignite a fire somewhere. Then the pressure is going to grow, and you will have a local expansion of gas leading to a flow from high to low pressure. So, and the left plot here shows an example of a resulting pressure field in 2D. Now remember, we are interested in the divergence of the pressure gradient. So first, what's the gradient? Now, the gradient for each point exactly shows in the direction in which the values increase most. So here on the right-hand side, we see the negative gradient, which shows in the opposite direction, so from high to low pressure. Now, what's the meaning of the divergence of this gradient? Please have a look at the direction of the individual vectors here in this red part. You see that the directions of all these vectors are showing outwards. They are diverging. This is a kind of source where the flow field expands. And this is just the meaning of a positive divergence. So on the other hand, in the blue part with the low pressure, all vectors seem to converge or contract inwards. This is a kind of sink. Here we have a negative divergence. And here in the middle part, there seems to be a balance between in and outgoing vectors. Here we have a divergence of roughly 0. So just to sum up, for each individual point, the divergence of the pressure gradient tells you whether your flow field expands or contracts there, and how much. So it is therefore something like an average rate of change for your flow field. Okay, in order to be able to calculate this equation on a computer system, it must be made discrete. And you know, to this end, the domain is covered with a rectangular grid, and the pressure values are only approximately computed in the cell centers. And for this purpose, as you can see here, the so-called 5-point stencil in 2D and the corresponding 7-point stencil in 3D is used, which calculates the value of the pressure in a single cell just as an average of its surrounding points and the force in this single cell. And if you do this for all cells of your grid, then you end up with a huge system of equations based on a matrix A, and this matrix has 5 or 7 times as much entries as you have cells in your grid. Now, the all-important question is how this equation can be solved as efficiently and as accurately as possible. And this is especially important because this equation must be solved quite often. You know that typical FDS simulations have tens of thousands of time steps, and in each of these time steps the system has to be solved at least twice. Now, in the following, I would like to describe 2 very basic design principles which underlie the different pressure solvers available in FDS. So let's first have a look at the difference between a structured and an unstructured grid. So in a typical simulation, you have your domain and you surely have some kind of internal solid cells within this domain. For example, you have walls, you have furniture, or whatever. Now, one big difference consists in the way in which these solid cells are handled. So please have a look at the following very small example with an internal obstruction on the left and the corresponding grid. And as already mentioned, the pressure values are computed in the cell centers. But what about these two blue dots within the obstruction? So in the structured discretization, no matter where you are in the domain, the same matrix stencil is used everywhere. That means it is used also in and along this internal obstruction. So the obstruction is somehow ignored, which on the first sight doesn't seem to be very physical. But as we will see, there are good reasons to do so. In the unstructured case, we use more intelligent matrix stencils, which exclude the internal obstruction and which really use the correct boundary conditions here, which on the first sight seems to be more correct. If you now look at the resulting matrices, you will find that they look quite different. So here in the structured case, the matrix has the same structure everywhere and is completely irregular. This has the great advantage that highly optimized solvers can be applied, which explicitly make use of these regular grid structures and which are extremely fast. In the unstructured case, the blocks look all different depending on the number of cells which are included to them. And this especially holds true if you have a more realistic geometry with much more internal obstructions. Now you get an irregular matrix. And for these type of matrices, you cannot use these highly tuned solvers, but you have to use much more robust solvers, which are usually not that fast. Another big difference is the type of data exchange. You know that typical FDS simulations are much too large to be solved on a single processor. So the geometry is subdivided into single meshes, which are then distributed to the processors of a parallel computer. But now the pressure solver has to be solved in a distributed way too. And for this reason, the processors must talk to each other and exchange information at coordinated time intervals. Now, the big question is, does a mesh only talk with its direct neighbors, or does it also talk with all other meshes? Because you can imagine that this will result in a differently strong degree of global coupling of the whole solution. But if you now look at the intrinsic properties of the pressure equation, this is a very important question. Remember that the single values in the pressure equation are defined as average values of their direct neighbors. So, if you now have a new information in some cell of your domain because you blow air into it or you ignite a fire, then this cell tries to be an average with all of its direct neighbors corresponding to the matrix stencil. And these cells in turn try to be an average with their neighbors. And so on until the boundary has been reached. And what's very important to note here is that this all happens within one single solution of the Poisson equation, which means that new information is spread immediately through the whole domain. Every single cell immediately feels and sees this new information. But imagine that you now have a very long domain, for example a tunnel, which must be subdivided into single meshes. Now this new information is initially trapped in the first mesh after the first Poisson solution and can only spread over to the next mesh when a data exchange has been performed. But if you only have local data exchanges, it can only reach mesh 2. So a whole sequence of successive local exchanges must take place until the information finally reaches the last mesh. So you have some kind of delay in information transfer. And if you only have a handful of meshes, then this doesn't matter. But if you have tens or hundreds of meshes, then this delay can lead to numerical instabilities, as we sometimes see in the discussion group for very long tunnels which are sealed, for example. So one way to get rid of this problem could be to distribute at least a basic global information across the meshes by the use of global data exchanges. And this exactly is the approach taken by some of the new experimental pressure solvers. So in the following, I will briefly illustrate the working principles of some selected pressure solvers which are available as experimental solvers in my SCARC class. And I will do it in a very illustrative and visual way. So unfortunately, I don't have the time to give you the whole picture of available solvers, but if you are interested in it, please have a look at my associated paper in which I will present them all. So you know that the default FDS pressure solver is based on the use of locally structured grids, which exclude the internal obstructions, and on every single mesh a local FFT is performed, which can be done extremely fast using the optimized crayfish package. And those single meshes are then coupled together by local data exchanges. And as you can see here, it's a structured approach with local data exchanges. But this procedure is not completely correct along internal obstructions, and there also might be troubles along mesh interfaces, so it may require an additional correction. So let me just give you an overview of an alternative solver, the so-called conjugate gradient method, which is available in my SCARC class. So this method does not really compute the solution to our system directly, but it makes use of the fact that this solution is also the minimum of this function. So don't matter the details, but starting from an initial guess, it generates a sequence of iterates which try to find the minimum of this function following the negative gradient, so the direction of the steepest descent. And this procedure really works for unstructured meshes. That is, it can handle internal boundary conditions correctly. And it is also correct at internal mesh interfaces because it really solves the global problem. But it needs many iterations. So although it's really accurate and robust, it's relatively slow compared to the FFT. And this is the reason that I also implemented another solver, which is based on the well-known multigrid methods. And these methods do not only use the original fine grid, but also a sequence of at least one or even more grid levels, which are getting coarser and coarser. And the idea behind is to be able to compute the basic global information, at least in a coarse sense, with less grid cells and less effort to finally get a much better global coupling of the overall problem. So in contrast to the geometric variants of this class, which do the coarsening only by doubling the grid size, this approach is more flexible. As you can see here, a collection of fine grid cells is combined to some kind of a cluster, an aggregate. And this clustering is done in such a way that it reflects the structure of the matrix stencil as closely as possible, which is important for the interpolation which has to take place between the grid levels. So the great advantage of this strategy is that it handles unstructured grids without any problem, in contrast to the geometric multigrid. But for sure it also requires global data exchange because it really solves the global Poisson equation. So in terms of numerical speed of convergence rate, it's very fast. It only needs very few iterations, but each iteration is relatively expensive because, as you see here, the data structures are more complex. So the implementation of this method, this was just my Corona home office job during the springtime. And believe me, this was a hard stuff to do. So currently I'm testing it, but I don't have a final picture yet, sorry. But as you can see here, it also works in 3D. And on the left-hand side here, you see a domain with a huge internal obstruction. So just for testing. And on the right-hand side, you see the corresponding coarsened grid. And if we look inside this grid, then we can see that it really perfectly matches this internal shape. And here I can really use the correct boundary conditions. So finally, I would like to very briefly present another method that I have also implemented on advice of Randy McDermott, and I'm currently testing it too. It consists of two parts for one Poisson solution. So in the first pass, a global solution is generated on the structured discretization, which has the correct external boundary conditions, but it's still not correct along internal boundaries. And based on this, a second pass has to be performed, which now is based on the correct internal boundary conditions, but with a zero external boundary. So if both solutions are summed up, we get really the global solution, which is correct at both the internal obstructions and along mesh interfaces. And you can see this at the very small example here, a square-shaped domain with internal obstruction, inflow from the left. And in the first pass, we get this structured solution, which doesn't know the internal obstruction. And in the second pass, we get a correction along the obstruction, and then we sum up both to the final correct solution. So finally, as some kind of a summary, I have only recently finished implementing the last two methods, and I will need more time and test series to make final statements about their efficiency. And again, there is still a lot to do, especially related to the runtime optimization of some parts of the code. But be sure I will report at the next FEMTC, and then hopefully again in a personal form. So this brings me up to the end of my presentation. I will summarize all this stuff in much more detail in my associated paper. So if you are interested, please have a look at it. And now thank you very much for your attention, and I'm happy to answer any questions you may have. Thank you.
So Kevin has a question, Kevin McGrattan. Is the last method you described exact?
Do you mean the Mckenney-Greengard-Mayo method? Yes, I think so. It's composed of two global Poisson solvers, a structured and an unstructured one.
Excellent, and he did confirm that, yes.
Interfaces, yeah.
Okay. Yeah, so yeah, that was the one he was mentioning. Randy McDermott just says, can you comment on the speed of the Laplace solution versus the Poisson in the MGM?
No, I'm sorry, not yet. What I can tell is that the structured solution, the global structured solution, is much faster than the unstructured one. So we really have the hope that we can optimize the whole stuff if we can exploit the fact that we only have few entries in the right-hand side for the Mckenney-Greengard-Mayo method. So, but I need some test cases to verify. Yes.
Excellent.
Second one is Laplace.
Mm-hmm. Let's see if we have any other questions or thoughts. I know this pressure solution is quite critical to sort of effective parallelization of FDS. Maybe, people have talked about massively parallel compute platforms like GPU systems and CUDA and all of these, where you have maybe thousands of processors or tens of thousands of meshes, and this global pressure solve and the local pressure solve and how this all ties together is sort of a critical component of being able to do that, like large scale. So
But I think the advantage is that this last method leaves some freedom to combine all the different iterative and direct solvers which we have already to get the best of it. Yeah.
That's excellent. It's great potential. And I'm always excited to see your talks each year. Like, what's happening now with the solver? What's Susanne up to today? Like, what's your work? So, let's see if we have anything else. Any other questions from the group? Just wait here. Okay. I think, here we have another one here. Randy just says, I want to comment that we have seen recent evidence that the pressure solver is not the issue with instabilities in long tunnels. One issue could be open boundaries. Any thoughts? And Randy just said, we have used MKL to check this. So
okay, that's very interesting.
Yeah, and Kevin just said one issue could be open boundaries. Any thoughts on that?
Mm-hmm. Not yet, sorry.
Okay. And have you looked at other numerical libraries like Trilineos, I think, Trilineos?
For iterative solvers, do you mean iterative solvers? Not yet. I worked with Hyper for a couple of months and also implemented some kind of interface, also based on algebraic multigrid.
And Randy's just mentioning the issues related to formulation, and they've added some guidance in the last user's guide about this.
Okay.
Wojciech says, do these different solvers require different levels of mesh quality in terms if we need to work with finer meshes to gain the benefits from the new solutions, or do the coarse meshes work as well?
No, they all start from the fine level which you get from FDS, and then they use additional coarse levels to better match the global data transfer. But the starting point is the original FDS mesh.
Have there, I guess, how does the work on the cut cell method, the newer cut cell method in FDS, the immersed boundary method, how will that impact this unstructured mesh of the geometry, around the geometry, I should say?
So I hope that I could incorporate it, because I do my own metrics, so I have to adapt the metrics anyway to the internal boundaries. So probably there could be some kind of interpolation. We would have to check that. Okay,
great. All right. Well, I think, it's a great talk as always to see an artist do their work.
Thank you. Thank you so much.
He does have one other question here. Do you consider how these solvers would work with very tall domains, like you would need in like a very massive fire or a wildfire, large-scale fire system scenario?
I don't think that this makes any difference.
Okay.
So I use the global solver anyway.
Mm-hmm. Okay, excellent. I think that's it then. Thank you so much for your presentation, for your time here for the Q&A. It's great chatting with you before this started, just to kind of catch up a little bit. So I wish you and your family well. Thank you, Susanne.
Bye.
Bye-bye.